Hello, my name is Sowmya Iyer, and this is my project presentation for the final project in CSCI-89B, Introduction to Natural Language Processing for fall of 2025. My project category is named Entity Recognition in Biomedical Texts. So the specific project title is Named Entity Recognition for Cancer Clinical Trials. I picked this because it is close to my domain of work, which is cancer computational biology. The motivation to do this is that we have some in cellular ex vivo data on cells on cell lines that that we were able to screen drugs on in a high throughput manner. So the goal is to see if we can supplement that experimental data with what we have evidence for from clinical trials. But clinical trial text contains rich and unstructured information. So you can manually extract drugs if it's one or two drugs at a time, or even a dozen or more. But for thousands and thousands of trials, it is not scalable to extract drugs and biomarkers. So the goal of this project is to automate entity extraction using the techniques we learned in natural language processing course to enable machine learnable trial outcomes. So the ultimate goal of this is to use these named entities as inputs to a machine learning model to be able to predict trial outcome. So data sources, what we did for these project goals, specific project goals, was to get this data source clinicaltrials.gov and identify cancer lineages, identify biomarkers, which are specifically gene mutations or expression levels or chromosomal rearrangements, identify drug names and combination therapies, and build a fully reproducible training and inference pipeline. So the source data sets. So we have for training clinical trial titles and descriptions from completed trials, which are phase 2 or phase 3 or phase 4 or approved approved in the market. The data set sizes for training, there were 47,447 unique sentences, and validation data was 5,272 sentences. They were jumbled in the sense that the brief title would come from one of the studies, and then the descriptions might come from another study. So the titles and the description were shuffled. And then training data was split into training and validation. But we do have a test data of 10,000 sentences, which the model has never seen before. It's held out, and it's from phase 1 and early phase 1 data. For labeling training data, we have tissue labels coming from pre-annotated list of known cancer lineages. This was just more like maybe 15 or 20 lineages, specifically, which I just put it in code. This doesn't need a huge database. For biomarkers, we have from this well-known, well-renowned, trustable data source called OncoKB, maintained by Memorial Sloan Kettering Cancer Center in New York. And we have a middleman database for recording gene fusion. So we get gene fusion data from the middleman database. Then as of drugs, there is a publicly available NCI cancer drug list. And there's also a PHRMA cancer drug set of drug lists, which are in trials. NCI only contains cancer drugs that are in the market. So when I did the first round of this, I saw that there were a lot of false negatives in especially for biomarker entities. And I realized that the training data was lacking in biomarkers, was very few in label counts. So what I decided to do was add my own training data because I know the labels, and I created 50,000 synthetic sentences using a combination of either genes or fusions, and also added one of like 7 or 8 random biomarker descriptors. So a gene name, say PDL1, and then it would say expression. So the synthetic sentence would read something like patients with high PDL1 expression were chosen for this arm of the study of doxycycline. So the random generation was also a control distribution where I try to reflect the distribution of fusion biomarkers as much smaller, and chromosomal deletions too are much rarer in the population than mutation and expression level biomarkers. So the majority of them are single gene biomarkers. And then augmenting for drugs. So the drugs that were already in trials were more or less established named drugs. They would end in like mAb for monoclonal antibody, etc. So I also, just to include more training, I added suffixes, specific suffixes to common just commonly known drug suffixes as regex patterns to find and training data. And I also added regex patterns for investigational drugs. So a combination of 3 to 5 letters followed by 5 to 10 digits. And then this regex logic was just directly integrated into label creation in the training data. Continuing on methodology, so the token level named entity recognition was using BIO tagging. So there's BI for tissue, BI for drug, BI for biomarker. And combination therapies were inferred computationally post hoc from clustered drug labels. So if there were 2 drug labels within close vicinity of each other, then they would be tagged as B combination and I combination. The reason this was done post hoc was if I were able to do, when I first tried to do just combinations themselves using conjunction words, etc., I wouldn't get individual drugs, which was also something that I needed. So I wanted to make sure that drugs were labeled separately than combinations. So the best way that I could think of was to do drugs first and then combine them later. I used this publicly available Hugging Face model by Microsoft Biomed NLP, Biomed BERT, base uncased. So this is on Hugging Face. I used a max sequence length of 128, ran it for 8 epochs with early stopping and best model saving, and I ran the training on A100 GPU on Google Colab. So what I have now is end-to-end reproducible pipeline, which has data preparation in it, tokenization, model training evaluation, and all of the dependencies with their versions are added as part of the submission. What I also did was provide an interactive inference app using Streamlit, which is something that I've never used before, so it was fun to do. Performance. So validation performance was extremely good. As you can see, it was close to 1. But on the test performance on unseen data, precision and recall were not good at all. In my opinion, I am not sure what the industry, like what the community standards are for NER, but it looks like this could use improvement. So some hypotheses on why test data perform so poorly. My first guess and the most probable thing is that the test data contains newer entities that the model has not seen during training. And this is especially possible because I'm thinking phase 1 and early phase 1 data are more likely to have newer drugs not already encountered and validated, and potentially new biomarkers as well. Entity misalignment was another hypothesis. So when I did some spot checks, there were a lot of instances where the label and either the start or end coordinates would match, but the other one wouldn't. And also the prediction might have, say, 62 to 67 as the boundary, whereas the true label would be 60 to 70 or 60 to 90. So in which case one would be a complete like subset of the other. But my metric calculation was very stringent. So everything needed to match, the label needed to match the start of the entity and the end of the entity. They all needed to match exactly. So there are papers that report based on sort of a proximity in terms of label ends and beginnings. But I wanted to start with the most stringent metric. I also think that the model should have been trained on data across all phases. So it learns all kinds of like new combinations of drugs and new drugs per se, which could be named differently than completed phase 2 trials. So my next steps are to improve the model. So I would like to retrain it with more data from across phases, include drugs and biomarkers from non-cancer trials as well for more robust training, and K-fold cross-validation during training. I just now run it once. The split just happens once. It would be more robust to get to do cross-validation and get precision and recall data. My goal is to get it to at least 0.75. That might be ambitious, but I'm shooting for that at this point. And the next step, after I get the model sort of robust and straightened out, I would like to use these entities as inputs to a machine learning model where I can predict trial completion from these entities, lineage biomarkers, and drug combinations. So I would like to end with some visual examples from the Streamlit app. So this is just, I put in some text from the test data. And as you can see that combination, this is a combination therapy. It also shows the word followed by as part of the combination. But that's just, that followed by was just, I guess, inferred as a drug. And here's another example which has tissue information in it, lung, and the particular KRAS mutation and a combination drug. This is a whole bunch of sentences that I put in to see like more data. And as you can see that there are drugs such as nivolumab, temsirolimus, and cyclophosphamide, etc., rituximab. And then you can also see interleukin-2, which is a gene biomarker. c-Met is a gene. And you can see tissues, various different tissues, ovarian, lymph, lung, esophagus, etc. So this one identifies single drugs as well as, this is to demonstrate identification of single drugs as well as combination in conjunction with tissue and biomarkers. So with this, I would like to thank the instructors and the TAs of this course for the immense knowledge that I have gained. Thank you so much for all your help. And I'm feeling extremely grateful that I can use this to make a real difference in patient therapies for cancer. Thank you very much.